Let's go again. So we stopped here, and I was telling you that some of the isotopic record we have in the very old rocks of the greenstone in Greenland, the greenstone belt in Greenland, they could be explained by abiotic reaction. Well, nevertheless, it looks like when you look at this secular evolution of isotopic composition that there is times in the geological record where things happen. And this is especially true around 2.7 billion years ago, where you see the average isotopic composition of the organic matter is dropping quite a lot, down to, for some example, less than minus 50 per mil, even minus 60 per mil. And that's something very remarkable, and that's something that we could discuss a bit. I need to center this again, like this, yeah. Okay, so that's basically the same picture, but it's not an envelope, but it's a real data point. Right, so we look at this excursion. So whenever you got a deviation from the average isotopic composition, we used to call that an isotopic excursion. Okay, so there is an isotopic excursion in the delta C13 signal of organic matter, down to minus 60 per mil. Also, interestingly, you see that there is no much variation of the carbonate isotopic composition. It's even clearer here. So organic matter is shifting its isotopic composition, but carbonate is not shifting its isotopic composition. Well, this is unexpected, right? It is unexpected because organic matter and carbonate, they are linked by the CO2 in the atmosphere. So if you change the isotopic composition of the organic matter, it means that the CO2 isotopic composition may have changed as well. And then the carbonate isotopic composition should also show a deviation from before. What hypothesis could we do for this? Well, easy. There is another source of carbon. And there is another type of carbon that goes into the organic matter. And this carbon is not producing carbonate. So if you mix normal CO2, the one that we always see, you produce a normal carbonate. Some of this CO2 is going into the organic matter. You mix that with a second source of carbon, and you produce an organic matter that have a mixed isotopic signature. And the easiest way to do that is to mix the CO2 with some methane, because methane have a very negative isotopic signature, like down to minus 100 per mil eventually, okay? So if I get back to that very simple sketch, it means that, well, we still have this coupling of producing carbonate, producing organic matter, but some of the organic matter is also recording another reservoir, which is methane, okay? So this has quite strong implication because it tells you that some of the organic matter is produced after methane at that very specific time. How could we do that? Well, there is at least two pathways. One is biological. You could produce organic matter by oxidizing methane with oxygen. This is called oxygenic methanotrophy. Methanotrophy means eating methane. But you could also do some methanotrophy, so taking methane into organic matter without oxygen, for example, using sulfate. Okay, and this is a very interesting metabolism, that one, which is called the anoxygenic oxidation of methane. And that's a metabolism that is really widespread, for example, in Black Sea or in deep sea ocean nowadays. Well, so that's a biological mechanism, but you could also think about an abiotic mechanism. And typically what happens on Titan, a satellite moon of Saturn, and there is a reaction in the atmosphere that combine methane and CO2, and that is able to produce tiny amount, tiny organic molecules. It's not tiny amount, actually, it's quite a lot. But you could produce tiny organic molecules. And well, in that case, I mean, if that happened on early Earth, I would give you exactly the same result, right? So you would have methane going into organic matter, going into sediments. Okay, that's an abiotic processes, but that's a possible processes. A lot of I don't have time to go into detail on that mechanism, but there was a lot of investigation to try to see if this reaction is possible on early Earth. Well, most people agree that it might not be sufficient to produce a lot of organic matter and the isotopic excursion I have shown you. But I could get back to that if you have questions later. So most people stick to the biological explanation for this isotopic excursion, and also because people have seen biomarkers in sediments of that age. So basically, if you take a sediment of 2.7 billion years, you measure the isotopic composition, it's very negative. You check at biomarkers, biomolecules, and you find that type of biomolecules that are typical of methane-eating bacteria. Okay? So that's two lines of evidence for the same biological processes. This biomarker stuff, it's very controversial though, but it's there. Okay, what does that mean? It means that this isotopic excursion at 2.7 billion years, they might be explained by oxidation of methane. You take a methane molecule, it's a quite reduced molecule, and you put this methane into organic matter. Okay, so you oxidize the molecules, basically. So what does it mean? Is that there is probably starting somewhere there more oxidants, or at least some oxidation reactions start at 2.7 and probably suck out methane that was in the environment at that time. Well, the next step would be eventually to see if we could try to give some hypotheses about those two reactions. This methane oxidation, was it mediated by sulfate or was it mediated by oxygen? And that's a very important question, because if it's oxygen, it means that the environment was already full of oxygen to oxidize methane. If it's sulfate, well, it means that you don't need a lot of oxygen. So that could be still an anoxic mechanism. You only need some sulfate in the ocean to do that. So in terms of paleo environment, that's really a big difference, those two hypotheses. How we try to address those two hypotheses? Well, we will use another isotopic system. We will use the sulfur isotopic system. Why? Well, because in this reaction, you see the sulfur is implied here, it's implied there. So sulfur may eventually track this reaction if there is a specific isotopic signature to that. And because in this reaction oxygen is involved, we could also use the sulfur isotope. Well, it's a bit different. I will explain you that. It's named the capital delta 33 sulfur. Okay, well, that's weird. But this is basically a record of the oxygen concentration in the environment. Okay? I will explain that to you. So we'll leave the carbon cycle for a moment and we go into the sulfur cycle. Okay? Sulfur have 4 natural stable isotopes. Sulfur 32, that's the more abundant, 95%. Sulfur 33, sulfur 34, sulfur 36. The most common ratio that is measured is the sulfur 34 over the sulfur 32 ratio. And yeah, and that's basically the geochemical cycle of sulfur today on Earth. What happened? Well, again, we need to know what is going from the mantle to the surface reservoir. So this is some sulfur that could be in form of SO2 or H2S. Well, speciation could vary, but anyway, the sulfur that is going from the mantle to the atmosphere its isotopic composition is somewhere close to 0 per mil. Okay? Yeah, and this is 0 per mil just because the reference for this isotopic composition is a meteorite. Okay? So the mantle has the isotopic composition of a meteorite, well, which makes sense. Yeah, and then the sulfur is in the atmosphere, and well, part of this sulfur will go into the oceans. Okay, so that's sulfate ions. And again, this sulfate in the ocean could escape the system, well, by precipitating different rocks. It could be sulfate rocks, so that's basically gypsum, evaporite, all the rocks that contain a lot of sulfate because of evaporation of seawater, like salt. And some of the sulfate could go into sediments as sulfides, so mostly pyrite. Pyrite is a mineral that looks like gold, and there is a lot of pyrite in the sediments in the oceans. Yeah, so if I again try to simplify a bit the geochemical cycle, just to make it more easy, you got some sulfates that arrive in the ocean, mostly from river, and some of this sulfate is precipitating as gypsum, so that's evaporite rocks like salt, and some of them precipitate as pyrite. Okay, so once again is one big reservoir and two escape routes for this big reservoir. So that's mostly the same. I mean, we could simplify, like for carbon, the system. We know what is going in the system. It's sulfate with an isotopic composition of around +3 per mil. Okay. Well, this is easy to do. Huh? You go to each river on Earth, or you go to Delta, it's easier, and you take some water, you measure the isotopic composition of sulfate, and you know what's the average isotopic composition of sulfate on Earth. It's close to that. And then evaporite is precipitating, so evaporite get enriched in the heavier isotope, +20 per mil, and some of the sulfate precipitate as pyrite, and the pyrite gets enriched in the lighter isotope, so it's -20 per mil. Okay? What's interesting there is, in order to precipitate pyrite, and all the pyrite you find in the sediments, it mostly comes from a very specific type of reaction that is mediated by a bacteria, which is called sulfate reduction bacteria. And this is the bacteria that converts sulfate into sulfide. Okay? And if you want to make this reaction, you need, obviously, to be in a completely anoxic environment, because you remove oxygen here and there, and if you are in an environment full of oxygen, it would be very difficult to remove the oxygen because there is a lot around. Okay? So this reaction that produces pyrite in sediments, it mostly comes from the activity of this very tiny bacteria. And it produces actually very nice shape of pyrite, which we call rhomboids. It's like a little framboise. Right. And again, I mean, this is like for carbon. We know what is getting in. We know what is escaping the system. So we could make an isotopic mass balance again. Okay. All the sulfate that is getting into the system is a fraction of sulfate times the isotopic composition of sulfate plus a fraction of pyrite times the isotopic composition of pyrite. Okay? And if it's steady state, like for carbon, well, you could get back to a very old type of sediments. Again, if I solve this equation, what I find is that today there is 40% of the sulfur that is entering the ocean as sulfate that is ending up as sulfide. Okay? That's a very strong biogeochemical reaction. 40% of the sulfate entering the ocean is processed by a bacteria and produce a mineral. That's a bit crazy, right? Okay, I skipped that one. If we look at the isotopic record through time, so exactly the same idea than what we have done with carbon, but the scale is the way around, I'm sorry. So old stuff are there. Oh no, that's the same way actually. Old stuff are there and nowadays is there. And you have all the isotopic composition that has been measured in sediment. Sulfates, so like gypsum, evaporites, they are in blue. And sulfide, they are in red, okay? What you see is that since like 500 million years ago, so since the Phanerozoic mostly, there is indeed a big difference between sulfate and sulfide. Sulfate are plus 20, and sulfide are around, in average, minus 20. So basically what I just show you. But if you get back to the Archean, well, sulfate and sulfide, they have almost the same isotopic composition, okay? So there is no isotopic discrimination or the distributions of isotope between sulfate and sulfide during the Archean, they are the same. What does that mean? Well, there is different way to explain that, but the most easy way to explain that is, well, if the sulfate concentration during the Archean is low, well, whenever you have a sulfate that goes into sulfide, because the sulfate concentration is low, the reaction would be 100%. Okay, so imagine you are in an anoxic world, there is a little bit of sulfate in the environment. It's very easy to reduce the sulfate into sulfide. So you will take all the sulfate and convert that into sulfide. But if it's a 100% reaction, there can't be any isotopic discrimination, right? Because you just take all the elements and you put it somewhere else. So there is no discrimination, and there is actually only one reservoir at the end, which is mostly sulfide. Okay? And that's so the very small differences in isotopic composition. So once again, here it's the differences between sulfate and sulfide is explained by small concentration of sulfate in the ocean. Okay? It does not tell you that there is no sulfate reduction. It just tells you that the isotopic discrimination associated to this reaction is hidden by the fact that the sulfate is fully converted into sulfide. Okay? Well, yeah. We stay there for the moment. The other thing is that because there is more than two isotopes, you could combine different type of isotopic composition. Okay, so that got a bit tricky, but you could measure the ratio of delta 34 over delta 32. That's the delta 34S, the isotopic composition of these two ratios. But you could also measure, if you want, the isotopic composition of the 33 over the 32, okay? So you could produce different deltas just because you have more than two isotopes, okay? You take a couple of isotopes and you have new deltas. That's very interesting, this thing, because if you take a sample, so each red dot is a sample. If you take a sample, it means that you have two isotopic information. You could measure, for example, for this sample, is delta 34S, so that's the ratio of 34, 32 is like minus 35, something like that. But on the exact same sample, you could also say, well, it's isotopic composition of 33, so that's the ratio 33, 32 is like is plus 20 per mil, okay? So you get an isotopic fingerprinting with 3 isotopes at the same time. Well, why it's interesting? Because if you look at these different measurements made on different type of samples, what you see is that all the points, they are lying on the same line. And this line is called the terrestrial fractionation line. And why it's always making a linear correlation? Well, that's easy to understand because this ratio is the 34 over the 32. So there is actually 2 atomic mass units between those 2 isotopes. And there, you measure the 33 over the 32. There is 1 atomic unit between those 2 isotopes. What does it give you is a slope that is 0.5. Okay, it's 1 over 2, 0.5 between those samples. Right? So that's theory. That's very easy. You get a slope of 0.5 because the isotopic differences depends on the mass of your isotope. Okay? And that's also called a mass-dependent fractionation line. All depend on mass. And this is always true. This terrestrial fractionation line, or mass-dependent fractionation line, it is reflected for all equilibrium fractionation. It is also reflected for all biological fractionation. So that's always the same. You always get this, nice correlation, and all the points are aligned on this terrestrial fractionation line. Well, so it doesn't look so much interesting then. I mean, why measuring this and this if you already could predict with the delta 34 what's the delta 33 rate? There's not really a lot of sense on doing that. The thing is, if you measure a sample that is not on that line, and this could happen, but a sample, for example, here that deviates from that line, you could scale this as the capital delta 33, which is what? Which is representing the deviation between the relationship that should link the 33 and the 34. So once again, the delta 33 should be scaled as half of the delta 34. Okay? If it's deviating from this, you could say, well, the capital delta 33 is not there, so it's not 0, is somewhere different from the normal relationship. Okay, I turn to that diagram. It's easier to understand that here. Red dot, so the normal line is this index is 0. Okay, so all is normal. The relationship is observed. If you measure a sample that is not on that line but is above the line, well, it means that the calculation gives you a deviation that is positive. Okay, and if you measure the way around, a sample that is below the line, it will convert into these measurements of the deviation from the normal line as negative. Okay? Well, okay, that's a lot of theory. Why it is interesting? It is interesting because we know only one processes that produce this non-zero capital 33. Okay, there is only one processes that could do that, or at least we only discover one processes on Earth that could do that. And to do this, so to produce mass-independent fractionation of sulfur, they are not dependent on mass, but something else. The only experiment that works is that you take a balloon, you put a lot of CO2, SO2 in the balloon, so sulfur gases, and you light that with UV. Okay, if you do that, you will start to do some photochemistry, and you will convert part of this SO2 into SO4, and part of the rest of the SO2 will convert into reduced sulfur, like elemental sulfur. Okay, and when you do that, you indeed produce mass-independent fractionation. So the more oxidized phases that you produce is getting negative, so that's the red dot here, negative cap 33. And the reduced phases would give you positive cap 33. Of course, if you mix that together again, you will get back to 0 again, right? But when you do that, photolysis on SO2, you produce mass-independent fractionation. So you produce deviation from 0 when you look at this cap 33. Why it's interesting? Because, well, the photolysis that work is a photolysis at 193 nanometer, and this is photochemical reaction that are scattered by ozone layer. So basically mean that if you have no ozone layer, you could have photolysis, UV photolysis, and you could split SO2 in the atmosphere and produce mass-independent fractionation. Whenever there is ozone layer in the atmosphere, the UV photolysis is blocked in the upper atmosphere. It will never reach the surface environment, and you will never produce mass-independent fractionation of sulfur, right? What does it mean? It means that you have a metric of the oxygen concentration in the atmosphere just by measuring the isotopic composition of sulfur. This is great. And that's the source reaction. But on top of that, there is also the fact that if you look at the sulfur speciation in the atmosphere, some of the volcanoes will release reduced sulfur, some of the volcanoes could release oxidized sulfur. But at the end, in the atmosphere, every molecule is mixing very rapidly. Just because when there is oxygen in the atmosphere, you will oxidize all these reduced sulfur phases, and you will have exchange with SO2. Some SO2 will be reduced back to sulfur. So there is a lot of reaction, and you will mix this reducer species with this oxidized species in almost no time. Okay, that's a very efficient mixing mechanism when there is oxygen. And the only time when this mixing of reduced and oxidized species is not efficient is when the oxygen concentration is below 10 to minus 5 the present atmospheric level. So 10 to minus 5 the concentration that is nowadays, less than a ppm of oxygen. Okay? And this is why it's a very interesting marker or chemical signature. This is because, well, to produce mass-independent fractionation, you need a source reaction with no ozone in the atmosphere, so no oxygen. But to preserve whatever mass-independent fractionation you have produced, you also need a very low level of oxygen. Otherwise, you will mix again all the signature. Okay? So there is two conditions that tells you, well, there is almost no oxygen in the environment if I got this signature different from 0. Okay? And what does it give you? Well, it gives you this type of picture. So that's the mass-independent fractionation record, the things that tells you there is no oxygen if it's different from 0. And you see there is a lot of those signatures until somewhere like 2.5 billion years ago. And after that, well, there is never mass-independent fractionation that I measure. Okay? It gives you what? It gives you there a time or a transitional time where the oxygen concentration may have rise in the atmosphere until at least a few tenths of ppm of oxygen. Okay? And this is what is called the great oxidation event. That's a very important thing in geochemistry. And yeah, basically tells you when the atmosphere of Earth gets oxygenated. Yeah, and of course it goes with some also mineral changes. For example, if here you see pyrites from rocks in this part of the diagrams, and if you get to that part of the diagram, you will get more and more rocks that is going into the sulfate part of the record. Okay, so only reduced minerals there, pyrites. Sulfate is completely converted. But after the oxygenation things, well, then sulfate could stabilize somehow in the ocean, start to build up in the ocean, concentration increase, and you could also produce some evaporite and gypsum deposit at that moment. So that is quite consistent with this story of the delta 34S. So those two stories, they are completely, fully consistent with each other. Okay, get back to that thing. So I got isotopic composition of sulfur that could eventually track the sulfate reduction reaction, the one that is done by bacteria. But I could also try to track this reaction just by looking if there is oxygen in the environment or not. Because if there is no oxygen in the environment, well, this reaction might not be possible. Okay? So people have done that in different places on Earth at this very specific age of 2.7 billion years. So that's the thing we try to understand. Tumbiana Formation, so that's in Australia, in the Pilbara Craton. That's a very nice formation. That's the one I studied during my PhD, actually. You see very nice stromatolites. That's mostly sediments, mostly carbonate. You also see ripple marks here. So you are basically, well, at the beach, right? You have sand, you have these stromatolites. It's a very nice outcrop with kind of easy geology to do. Shallow marine environment. And those rocks, they are not too cooked, actually. They are in what we call the green sheet fascias, which mean less than 200 degrees or 250 degrees maximum. So, well, I mean, it's cooked, obviously. But it's not like the Greenland rocks we have just seen at 600, 800 degrees. It's a little more gentle or cooler temperature. Same age in other places, the North Atlantic Craton, the Kidd Creek Formation, so that's the Abitibi in Canada. Well, the rocks are a little less impressive there, but they probably reflect a quite deeper depositional environment close to hydrothermal system, so that might be interesting to also track what happened in the deep ocean. And yeah, again, metamorphism is not too high, and in that case, it's mostly clay layers. So that was carbonate in the Tumbiana Formation. There, it's more shaly stuff. And the Cheshire Formation in Zimbabwe, so we try to cover a lot of different places. And in that case, again, it's stromatolite in carbonate platform. Shallow marine and pretty much the same condition like the Tumbiana Formation, actually. So if I look at the Tumbiana Formation, well, once again, the C13 was very low, minus 33 per mil. So that's fine. That's exactly what we try to understand. And I skip that one. If you look at the sulfur record, so in that case, what people have done is directly measure using an ion microprobe in thin sections, very small pyrite. Okay, so you take pyrite, you use a microprobe, and you measure the isotopic composition on the very small, tiny grains of pyrite. And then you have isotopic composition distribution, okay, along this thin section. And that was mostly done on thin section that comes from stromatolitic layers. Well, when you look at that, you see that there is, so that's a statistical distribution here. You see that there is a bit of variation, actually, from minus 30 to maybe something like plus 50. But 80% of the distribution is explained by value that are very close to 0 per mil, okay? So there is no big range of isotopic fractionation. I mean, the isotopic composition of those pyrite, they are just quite close, actually, to the bulk Earth or meteorite stuff. There is no big clue of a bacteria having processed this, this element. If we check at the CAP33, so that's the metric of is there oxygen or not, you see that it's not 0. It's somewhere between minus 0.2 and plus 1 something. Okay, so different from 0, it tells you that, well, this is like what we see all over the Archean until the Great Oxidation Event, there is no oxygen. Or let's put it that way, oxygen concentration is below 10 to minus 5, the present atmospheric level. Okay, almost no oxygen. So that reaction might not really be efficient, okay? And yeah, most people would agree that oxygenic methanotrophy is probably not a reasonable hypothesis at that time, just because there is no oxygen. Although that reaction is not really well demonstrated, right? Because we don't see a big sulfate reduction fractionation. Let's go to Kid Creek formation in Abitibi. Again, delta 34S, so the metric for sulfate reduction, well, there is no big fractionation. And obviously, there is no pyrite grains with isotopic composition of minus 20 per mil, like we see nowadays in the sediments. Okay, so this reaction is not really seen actually in the sediments. And this metric, the CAP33S, the mass-independent fractionation stuff, different from 0. Okay, 0 is there. You see it's varying from 4 to minus 1 point something. So very low oxygen concentration as well, like for the Tumbiana formation. Okay, one more example, Cheshire Formation in Zimbabwe. Again, for this formation, if you look at the organic matter, well, you got this very negative value, right? Some are down to minus 50 per mil or close to 50 per mil. So you have this methane signal in the organic matter. And for the delta 44S and CAP33S, well, that one is a bit interesting because there is no much, but there is a few data points that is getting to very negative value, right? Well, it's only 2 points, it's not much, but still there is a bit of those sample that gets to a signature that resembles sulfate reduction. And it was also measured by an older study actually with value down to minus 18 per mil, minus 20 per mil. So again, the distribution is centered around 0. But looks like actually that some pyrite grains, some of the sulfide grains, they show negative isotopic composition that could be compatible with sulfate reduction. The CAP33 signal, so the mass-independent fractionation stuff, again, I mean, it's pretty clear. There is no oxygen in the system because we preserve this mass-independent signal there. So what's the conclusion there? For those 3 examples, we got negative isotopic composition of carbon that is compatible with methane cycling. Methanotrophy is there at different places on Earth at the same time. Okay, so that might be a global thing. Maybe the sulfate was the electron acceptor in this reaction that could oxidize methane into organic matter. Maybe, okay, but there is no real clue on that, or it's difficult to be sure about that hypothesis. But what we know for sure is that this is not due to oxygen. So the methane oxidation was probably not mediated by oxygen at that time. Okay. Well, the other thing is that this specific metabolism, methanotrophy, the microbiologists, they work a lot on that, and well, because it's a quite interesting metabolism, because it's taking a very strong greenhouse gases into a stable molecule, which could be interesting for climate questions. Anyway, this process of anaerobically oxidizing methane, it could be done by sulfate, but it could be done by a lot of things actually. Iron oxide, manganese oxide, and every molecule that have a bit of oxygen could eventually help to do methanotrophy. Okay, so there is much more to explore actually. And this is what some people have done there. So that's again Tumbiana formation, and people have measured the isotopic composition of iron trying to see if, well, if it's not sulfate reduction, could be eventually iron reduction. And again, another isotopic system, and we try to see if isotopic signature is compatible with what we could have in batch culture experiments in the lab, for example. Okay? And so on and so forth. I mean, just continuing trying to see which reaction could work eventually. Okay. In both cases, if we go in if we put on a redox later the different reaction that could happen, well, this is the first reaction that may happen, oxidation of methane, okay, into an oxidized molecule, and this is what the delta C13 is eventually recording. Sulfate reduction, eventually possible, but the delta 34S signature is not that demonstrative of that processes. Although, if you take the redox couple on top of sulfur on this later oxidation of iron 2 plus into iron oxide, iron 3 plus, well, this is something that is really well known in the Archean, because we have tons of sediments like that, which are sediments made out of iron oxide, okay? And this is, I mean, you don't need isotopic composition there to understand that we have oxidized and rust the ocean at some points and produce a lot of iron oxide in the ocean. So in a thermodynamic perspective, on this redox later, if this happens and if this is widespread, well, this is very much possible as well. Moreover, on top of that, people also measure the isotopic composition and make some secular evolution of isotopic composition. And that's the same story, actually. You see that the isotopic composition of iron show a negative excursion, so a big changes, an isotopic excursion, right at 2.7 billion years ago. Okay, so right at the same time, the iron isotopic composition of the ocean changed a lot. Okay, which suggests that all these reactions turned to be very effective at that time, and a lot of redistribution of, well, elements obviously, but isotopes as well. Okay, one last thing we could do together is, well, if those three redox couple is functioning, one could also ask, well, and we are not there to oxygen because we just said that there is no oxygen, but what about nitrogen? Which, I mean, we get closer to oxygen, right? We know that there is no oxygen, but until when up in the redox later we could approach the oxygen? So, well, you could wonder about the nitrogen isotope signature of the rocks of this age. Okay, so that's another biogeochemical cycle. That's another lot of work again to understand how it works exactly. We'll try to make it very simple together, okay? Because this is probably even more complicated than the sulfur isotope stuff. The nitrogen biogeochemical cycle is quite a complicated one. So what do we have? We have nitrogen in the atmosphere, okay? And some of this nitrogen could enter the system during nitrogen fixation. And it will be converted to ammonium, and this ammonium will be used by microorganisms and produce organic nitrogen. Some of this ammonium, it could be oxidized back to nitrite and then nitrate, okay? And some of this nitrate, it could be eventually reduced again by a process that is called denitrification. And that's a whole cycle that is more or less steady state, okay? Well, that's a very difficult one. What you need to remember is more easy than that, actually. You need to remember that this is the main reservoir on Earth, nitrogen in the atmosphere. you need to remember that finally what we see in that cycle is that there is a very reduced molecule, ammonium, there is a very oxidized molecule, nitrate, okay? Oxidation state -3 +5. That's a very big difference in oxidation state. Okay. The main input in the ocean is just fixation of N2 into the biosphere. Yeah. Most of the fixed inorganic nitrogen in the ocean is in that form, nitrate, and the flux that is getting back nitrogen into the atmosphere is due to denitrification, so through this reaction, okay? The thing you want to remember there is that all the blue arrow, this is the processes where there is no fractionation of isotopic composition. Okay, so basically all these processes we don't care about. There is no fractionation that's associated to that. That's cool because, well, then there is ammonium that could come from N2 from the atmosphere. Okay, so part of the ammonium that goes into the organic matter is coming from N2, and part of the ammonium is coming from nitrate after denitrification. Okay? So it's basically, it's a way to simplify that. Most of the nitrogen in organics, it comes from the atmosphere, or it comes from nitrate. Okay? Wow, that's a bit easier to understand. Okay. When you come from nitrogen from only, if your nitrogen come only from fixation from the atmosphere, the isotopic composition you have is close to 0 per mil. It's close to the atmosphere. And if you use nitrogen to build your organic matter from nitrate, you will get an isotopic composition that is positive, okay? And it could be positive like +5, or it could be +10. Why it's changing? It's changing because it depends on how the nitrogen was depleted by denitrification. So you have a pool of nitrate. Its isotopic composition is increasing if the pool of nitrate is shrinking due to denitrification. Do you follow me? Maybe. Okay. How does it work? Well, it works like the isotopic composition of nitrogen in the global ocean today is fully reflecting the oxygen concentration of the surface layer of the upper 200 meters of the ocean. So that's exactly what I told you. If the nitrogen pool is shrinking in the ocean due to denitrification, the isotopic composition is getting higher. Okay? And you see that here, very high isotopic composition here or here. They are in oceanic basin where the oxygen concentration is very low. Okay? Why? Because low oxygen concentration means less nitrate. Okay? And less nitrate means bigger isotopic composition. Okay, so that's the only thing you really need to understand actually. Few complications if you get back to the Archean. One complication that did not really happen with carbon and sulfur is that for the Archean, the isotopic composition is evolving a lot with metamorphism, okay? And basically, hotter you cook your rock, so warmer temperature is getting, and more the delta 15N is getting heavier. Okay, so that's something to eventually take into consideration. The isotopic composition of nitrogen is evolving very rapidly with temperature compared to carbon and sulfur. And another thing that we need to hypothesis there is the isotopic composition of the nitrogen in the Archean, if we want to interpret Archean rocks. And we don't know actually the isotopic composition of the nitrogen in the atmosphere of the primitive Earth. There is only one measurement that has been done on some quartz deposit from 3.5 billion years ago. And in this quartz, they look at fluid inclusion, so very small atmospheric bubble, and they measure the nitrogen isotopic composition of this bubble. They find 0. Okay, so they say, well, 0 at 3.5, 0 nowadays. It was 0 forever. Okay, well, that's not a big constraint. But that's mostly like what cosmochemists are doing with meteorite. One model with one data point. Okay. Well, but that's a very important hypothesis, right? Because if you don't know the isotopic composition of the starting things here, you can't really resolve all the cycling of nitrogen. Right, so two main hypotheses that are easy to understand. Know if there is no oxygen in the system, there is no nitrate in the system, so all the nitrogen comes from nitrogen fixation to ammonium to organic matter. One little thing that is a little unclear yet is there is ways to fix nitrogen abiotically, so nitrogen fixation producing organic matter without passing through nitrogen, biological nitrogen fixation. That's photochemistry, that could be lightening as well, that fix a bit of nitrogen. Well, that's actually the way you produce ammonium for rice culture, for example. You use a process that is called Haber-Bosch, and Haber-Bosch fixation of nitrogen is just fixation of nitrogen by lightning, basically. And we don't know so well the isotopic composition of this. One last thing is also that some ammonium in very specific conditions could escape to the atmosphere as ammonia. This happens very rarely, but it could happen if the pH of the water is getting more than 10. Okay, so hyperalkaline water, they will lose a bit of ammonium as ammonia. They will decas ammonia. Okay. Yeah, and if there is oxygen in the middle, in the ocean, well, this nitrate could eventually build up in the ocean, and in that case, the isotopic composition will reflect the intensity of that denitrification process, okay, and get printed in the organic matter. So this isotopic composition depends on if this denitrification is fast or not, and goes in the organic matter. But in any case, it will not give you 0. It will give you +5 or +10 or plus something, but not 0. Okay? Well, that's another way to show you what I try to demonstrate. If you look at a sediment and you measure the delta 15N, the nitrogen isotopic composition of a sediment, it will mostly reflect how the nitrogen gets incorporated into organic matter, so primary producer. And if it's N2, the molecule, the original molecules, it would be around 1 per mil. If it's nitrate, it would be somewhere between 30 and eventually close to the N2 isotopic composition. Okay. So finally, measuring the delta 15N would give you an idea of the source molecule, either N2 or nitrate. Okay, that's a long introduction. And if we look at the isotopic composition of nitrogen for the Tumbiana formation, and we ask the question, well, is there any nitrate or oxidized nitrogen molecule? We want to measure the isotopic composition. And when we do that, well, you see the result. There is a lot of variation, but the average is around +20 per mil, and the range of isotopic composition is very huge. I mean, it's +8 to +50 per mil. Okay? That's really a lot. That's AV isotope only in this system. How do we explain this AV isotope? Well, it can't be only nitrogen from there, because it gives you a signature of 0. So it means that some of the ammonium was converted to nitrate, and some of this nitrate was getting back to the atmosphere. And you got enriched value up to plus 50 per mil, which is really, really a big fractionation. Okay? That's an hypothesis, but there is another hypothesis, actually, to explain this very high value, which is the degassing stuff. Okay? So maybe, or it could be that the Tumbiana Formation was in an environment where the pH of the water was very high, okay, like more than 9.2 or around 10 or 11. For the Tumbiana Formation, this hypothesis could eventually make sense because if you look at thin section, you have evaporite, so this is an alide crustile, there is stromatolite, but there is a lot of recrystallization of carbonate and stuff like that. And actually, the sediments could have very been precipitated into a lake, a big lake, like a pond, okay? And in a big lake, you could have a pH that goes very high, eventually. So that makes, that's an hypothesis that is possible, actually. Moreover, if you look again at a compilation, so that's nitrogen isotopic composition through time. So this time, this is all those things are there. Great oxidation event, and again the 2.7 things. So, I mean, there is an isotopic excursion for nitrogen, but on that diagrams you see that there is only the Tumbiana Formation that show this, which is not a lot actually. It's only one example with very high isotopic composition. And yeah, you don't really know if it's because there is some nitrate accumulation or because of pH, if you cannot exclude completely the pH. Once again, it means that if the Tumbiana Formation is that type of pond, close to the ocean but not really in the ocean, so that's an example in Tunisia here of a sapcra environment, a very evaporative small pond close to the ocean. Well, of course, you will tell a story that has nothing to do with what really happened in the ocean, right? So we need to continue on those two hypotheses, or to testify these two hypotheses recorded in the ocean. And that's what has been done with another formation in Brazil. And so that's, you see, mostly same ages, around 2.7 billion years ago. But this formation, the model of sedimentation is pretty clear. I mean, this is abyssal plain with turbidite. There is banded iron formation. There is conglomerate. There is all the sediments you expect on an ocean margin. So you are sure to be in the ocean. That's also interesting because you are in the ocean, and we also know that the pH of the ocean between 2 and 3 billion years ago is mostly around 7, okay? So the ocean have a neutral pH during the Archean most of the time. And you cannot think about the ocean having a pH of 10 where ammonia degassing is triggered. That would not make sense compared to what we understood of the paleo environment. Meaning that if you look at this speciation diagram, you will be in a range where there is only ammonium, and you will never go to that pKa of reaction point where ammonium is getting lower and ammonia could be converted into the solution. All right, so simply, if you measure the isotopic composition in this formation, well, you get isotopic composition, again, that are very heavy, like plus 30, between plus 30 and plus 40 per mil. The pH is not high enough for ammonia degassing, so, well, the best explanation is there is some nitrate accumulating in the ocean starting somewhere at 2.7 billion years ago. Okay? Yeah, so it gives you, at least for the nitrogen cycle, the idea that early in the Archean, the speciation was probably mostly dinitrogen ammonium. Somewhere there, you have dinitrogen ammonium plus nitrate, but the nitrates stay cryptic. It's not accumulating. There is just some nitrate process in the water column. And after the great oxidation event, obviously you start to have both speciation, ammonium and nitrate, and somewhere close to the modern oceanic world, you will have nitrate as the main reservoir in the ocean. Okay, so small increase or passing from ammonium to nitrate, and probably with the triggering reaction starting there at 2.7 billion years ago. Okay, so that's the conclusion to, if you look at, if you look at, if you look at the isotopic composition of nitrogen in Archean sediment, you get a picture of increasing redox processing of nitrogen, increasing nitrate concentration starting at somewhere like 2.7 billion years ago. And if I summarize, finally, what we have seen together, exploring a little bit of the Archean sediments, is that, well, at 2.7 billion years ago, so some like 200 to 300 million years before the Great Oxidation event, we have seen carbon isotopic excursion, nitrogen isotopic excursion, and all these excursions tell us the same thing. We are processing some reduced reservoir into more oxidized reservoir, okay? We have seen together that the mass-independent fractionation of sulfur, they disappear at the Great Oxidation event. Okay, so this is really where sulfur told you it's getting, the atmosphere is getting oxidized. So we got oxygen in the atmosphere. Yeah, and we have seen that later in time, the delta 34S is showing that sulfate concentration is slowly building up in the ocean, okay? And we have seen that picture where the two records of sulfate and sulfur, they are, splitting from each other slowly and slowly into the Phanerozoic, okay? Yeah, so what does all these things track is planetary oxygenation, basically. And what I have tried to demonstrate and show you is that this planetary oxygenation is, at least for part of it, due to biospheric evolution. Okay, with new metabolism getting in place and making new distribution of elements or new distribution of isotopes between reservoirs. And the one we could check as a geologist is sediments. Okay, so we see differences in sediments that show you that distribution from ocean atmosphere to sediments is changing. Due to what? Due to redox speciation changing. Due to what? Due to biospheric evolution. And that's it.